To see everyone up front. This session is recorded, so you never know what will happen with it. We're just waiting 1 more minute to see if there are more people coming in. Anyone waiting to come in, Anna? Okay, so we wait for the other Anna. And what we want to say at the very beginning is a big thank you to Universitat Politècnica de Catalunya and to this School of Telecommunications and Aerospace Engineering for hosting us and for having a working air conditioning. We want to thank all the partners of this event today. There are many people who have helped, as you can imagine, with the planning, the coordination, many volunteers. No one gets paid a salary, except for the catering people. And I hope you enjoyed the coffee break. That was sponsored by the event sponsors, and you've seen the logos all over. So some people do get paid, of course. But our main speaker now, the keynote speaker, is not paid. He comes because he loves coming here. Are we talking about you? Yes? So, astronaut Jeff Hoffman.
At least you're going to give me lunch.
Yeah, but we don't consider that a salary. We are so thankful that Professor Jeffrey Hoffman, or Jeff, as most people call you, has decided to take a plane and spend the whole night on board. He just landed this morning. From his hometown of Boston, Massachusetts, where he is professor of the practice of astronautics at MIT. And MIT, as you know, is a sister university to UPC. They're both on the top of the list. And Jeff studied in many different places, the United States, in the UK, and he did his PhD at Harvard, also in North America. His main specialty, at least at the beginning, was astrophysics. And you designed, you built, you operated experiments to do with X-ray astronomy and gamma-ray astronomy. So those rays that are really bringing useful information to us. And one of your experiments even flew on board the space shuttle. Have you ever met someone who has flown 5 times on the space shuttle? Maybe not. Well, today we have Jeff, who has flown 5 times. And that includes 4 extravehicular activities. So he went out and came back 4 times. And of course, he's world famous for one of those, which thankfully repaired the Hubble Space Telescope. And this was reminded to me earlier today by Professor Jordi Gutiérrez, who said, he saved Hubble. We should make him a monument. But Jeff has saved many other things. Can I ask for a raise of hands? How many people in this room have listened in person, not online, to a previous lecture by Jeff Hoffman? Who has been, okay, 1, 2, right? I know there are more people around, but they're not in this room right now. I can recognize the 2 who raised their hands. They are both alumni of the International Space University, where Jeff has been lecturing since 1993. And that was in Houston at this itinerant summer school on space. And in 1994, Jeff came to the ISU in Barcelona. That's where Jordi was. Do you recognize your former student?
It's been a while.
He had a bit more hair at the time.
So did I.
So did you. So have you met someone who has flown 5 times? At the same time, he speaks 5 languages. And I will pass the mic to Jeff now, with the first question. What are those languages? And then maybe you want to talk to us about your Hubble repair. Jeff, give him a big applause.
Well, you asked for my languages, so I do speak a little English, Español, Deutsch, Français, et un po' Italiano. I at one time spoke some Russian too, but I've kind of forgotten that. But anyway, I only have 30 minutes, so I'd like to give you kind of the highlights of what we did with Hubble, because of all the things that I did in space, that was certainly had the most lasting significance. Hopefully I don't have to spend a lot of time explaining why we like to put telescopes above the atmosphere. I mean, it's a lot more expensive to put something up in space. But of course, if you want to look at ultraviolet light, infrared light, things which are absorbed by our atmosphere, and if you want to get rid of the distortions that our atmosphere creates, it's worth spending the money to put a high-quality optical telescope in space. And that was the dream of Hubble, but it went beyond that. Telescopes on the Earth, obviously if something breaks, you can fix it. But the critical thing about a telescope on the Earth, a large telescope, you build a mirror and it's good for decades. I mean, but the instruments that you put at the focal point of the telescope, that technology is constantly improving. And so the idea behind Hubble was they wanted to make it like telescopes on the Earth, where you could service the telescopes and continually upgrade the instrumentation. This had never been done before in space. Of course, designing a telescope that was serviceable was something new. It was a lot more difficult, and as with many space projects involving new technology, Hubble was behind schedule, above its budget, but it finally did get launched in the spring of 1990, and presumably you all know the story that, despite, there was a big build-up to all the great things that Hubble was going to do and change our view of the universe, and it couldn't focus properly. It was a absolute disaster for NASA, for the astronomical community. Congress was furious with NASA. They were holding up the money that was eventually going to go towards the space station. So what do you do when you have a disastrous problem like that? Well, the first thing you need to understand, how did this happen? And I'm going to show you how it came about. And this is something that even a lot of astronomers, everybody knows that, the mirror was not quite the right shape. But how could that have happened? Well, here's the basic optics of the telescope. The light comes in, bounces off the primary mirror, off the secondary mirror, and then you have a lot of instruments back here, each of which has a little 45-degree mirror which goes into the light and reflects it into the instrument. And this gives you a sense. So the mirror is kind of up around here, and the instruments are in the back, and most of up here is just empty. So when you're making a big mirror, Hubble was made with the telescope technology of the mid-20th century, just like the big Palomar telescope. You start with a big chunk of glass that's flat, and then you gradually make it into the right shape by, cutting away grinding away the glass. And you need to measure the shape of the mirror while you're doing this. And to do that, they install a kind of a mini telescope. It's called a corrective null corrector. I won't go into the details, but the point is it has to be positioned exactly at the right place with respect to the focus of the telescope in order to do its job properly. If you look here, there's this big measuring or metering rod with an end cap at the top. So the deal with that is that end cap had a small hole in the middle of it, and they could shine a light down that would reflect from the top of the metering rod, and that would tell you that you're at the right position. And they were a little bit concerned, maybe some of the light would reflect off the top there, and so to avoid that, they put a special anti-reflective coating. That way they would be sure that any light that was reflected would be reflected from the top of the measuring rod and not from the end cap. Well, after Hubble was launched and we knew there was a problem, they went back to the factory where the mirror was made, and they found that end cap, and wouldn't you believe it, bad luck. Some of that anti-reflective coating had basically worn away. And so what had actually happened, on the left is what they thought they were looking at. On the right is what they were actually looking at. When the technician installed that metering rod, he said afterwards, yeah, I had trouble getting that thing in. I had to put in some shims. I mean, that should have raised a big red flag. There were lots of red flags all along this process, and they were kind of ignored. And it's a good object lesson for all of you students. Whenever you see something that looks like there may be a problem, you can't just sweep it under the rug, and you have to pay attention to it. But just a lot of bad luck. I mean, it turned out that 1.3 millimeters was exactly the same distance here. And so it looked like they had positioned the rod perfectly, whereas in fact it was off by 1.3 millimeters. And the net result was that the shape of the mirror that was measured was not what it should have been. The mirror was slightly too flat. In the end, a little bit too much glass was removed from the outer part of the mirror compared to the inner. How much? About 1.5 microns. So, your human hair is about 50 microns. So, a 20th of the diameter of a human hair. But the optics of Hubble were so precise that made all the difference. All right, so we know what the problem was. Then the critical thing was, could we fix it? And here's how the fix was done. Every one of those instruments, like I said, has a little, we call it a pick-off mirror, a 45-degree mirror that goes out into the light that's coming down from the secondary mirror. And what we had to do was to, first of all, for each of these instruments, we had to install 2 tiny little corrective optics mirrors about the size of your thumbnail. The first one would block the out-of-focus light that's coming into the mirror, reflect it up to a second mirror which was slightly curved to compensate for the lack of curvature in the primary mirror, and then reflect that back into the scientific instruments. This is just a schematic. It's, as you can imagine, it was a lot more complicated. It was a real tour de force of optical engineering, mechanical engineering, electrical engineering. But we were pretty convinced that we understood what the problem was and we know how to fix it. Now, back in the astronaut office, for our point of view, this was a primo mission, and everybody was wondering, you know, who's going to get to be on the crew. Because Hubble this was such a critical mission, NASA wanted to do anything possible to reduce the risk of failure. And one of the things they decided was, since this, the corrective optics were only part of the problem, there were a dozen different things on the telescope that needed to be fixed. And when we actually did the analysis, it was going to take 5 spacewalks. NASA had never done 5 spacewalks in a mission. 3 was the most we had ever done before. And they decided that only people who had previously done a spacewalk would be eligible to service Hubble on this first critical mission. And it turned out, by chance, on my very first flight, I got involved in what was the first ever unplanned spacewalk that NASA had ever done in its history. We went out, we built those little tools which we attached to the end of the arm, and we used that to fix a malfunctioning satellite. So anyway, I was fortunate enough then to get onto the crew, and you know, tremendous amount of training both for the robotic arm. We were the first crew that introduced virtual reality as a significant part of our training. But certainly for the 4 of us who were doing spacewalks, and they decided that with 5 spacewalks, they wanted 2 teams. So I would go out on days 1, 3, and 5 with my partner, and the other team would go out on days 2 and 4. Because the length of the mission meant that we didn't have any rest days between the spacewalks. We had to do them day after day after day. And they figured 5 spacewalks maybe in 5 days was maybe too much for you know, 1 team. So we had 2 teams of spacewalkers. And we spent a lot of time underwater, 400 hours total, I think, of water time. But it's absolutely critical because the limiting factor, you know, on every mission you talk about a limiting consumable. It may be oxygen, it may be electrical power, whatever. For us, the limiting consumable was the useful EVA time that we had to go out and fix Hubble. And so we practiced over and over to get all of the things that we were going to do, that we could do it as efficiently as possible. And of course, when you're working in the water, you have a lot of viscosity, and you move these large objects around. In order to help us get the feel for what it's really going to be like, they put us on an air-bearing floor. And here I'm moving that same piece of equipment with the same mass and moments of inertia, but we're both, at least in 2 dimensions, completely frictionless. So you really get the sense of you can move around large objects just with fingertip pressure, and you have to learn how to control those. And we also, of course, spent a lot of time up at the Goddard Space Flight Center, where we could look at the real instruments that we were going to put in, not just the models in the water. So down to the Cape in our T-38s the night before launch, and we had a launch video which doesn't run on the HDMI here, but we did get up in space. We launched at 4 o'clock in the morning. A lot of our launch guests complained. They said, "Why do you have to launch at 4 o'clock in the morning?" Well, you're doing a rendezvous. So, you know, a few minutes before we launched, Hubble flew over, and my brother looked at it and he said, "Well, yeah, that's Hubble. I guess NASA knows what they're doing, you know." And so, yeah, we launched at 4 o'clock in the morning, and we get up. The airlock was built for 2 spacesuits. We had 4 in there, so it was pretty crowded. This is how we protect our sensitive equipment from launch. And the tools that we took were absolutely critical for this. We had a lot of specialized tools. about 200 in all, maybe half of which we were planning to use, and a lot for backup. And we spent the first evening just checking out our spacesuits. And of course, your spacesuit, it's like a miniature spacecraft. It's got to provide you with oxygen, with pressurization, with thermal control, with communications. Your life depends on it. You want to be sure that your spacesuit is in good working shape before you go out. Here I'm putting in the battery. And then getting up in the morning, I'll have a big breakfast because I know I'm not going to have anything to eat for the next 8 hours or so. We were up pretty high, as high as the shuttle ever went. So we were closer to the Van Allen radiation belts than any other flights of the shuttle, and so they had us wear special radiation monitors, which you can see patched on. We put on long underwear so that we can stay warm during the nighttime when it gets really cold, and then on top of that, liquid cooling garment, which will keep us cool when we're in the sunlight. I mean, the difference between sun and shadow when you're in space is huge. And this allowed us to stay comfortable the whole time. So into the spacesuit, it's a tight fit. You get in. We then have to basically breathe pure oxygen for about 40 minutes to complete the denitrogenation of our blood, so that when we take the spacesuits down to 0.3 of an atmosphere with a pure oxygen inside, if you didn't denitrogenate, you're going to get the bends, just like a scuba diver who comes up too fast. So, just getting a big circle. Okay, there we go. So I'm not going to show, I just don't have time to show the details of how we did all the fixes. It's been pretty well covered in TV shows and the like. Hopefully you will have had a chance to see this. I've been trying to give you more of the personal view of how we found out what the problem is and how we trained for it. But just a couple of pictures of what it's like being out there. I had just installed the new wide field camera, which the WIFPIC 2, so to speak. This is the old one, which we took out and brought back home. And that WIFPIC 2 is responsible for a lot of the iconic, famous pictures that Hubble has produced. This is an astronaut's view looking up at Hubble. It's pretty big. It's about 15 meters from bottom to top. And basically, we were able to do all of the tasks which were set up and left Hubble with new solar arrays. And we knew that everything we had done had worked. What we didn't know is, would the corrective optics really correct the optics? And you can't turn on the instruments right away. You've launched stuff from the Earth. There's atmosphere that is adhering to the outside, and you have to wait about 2 weeks for everything to outgas before you can turn the high voltage on. Otherwise, you're going to get sparking and you'll blow your electronics. So it wasn't until, I'll never forget this, it was New Year's Eve. We had a party. I was just cleaning up. The phone rang. It was a astronomer friend of mine from the Space Telescope Science Institute who, we wished each other a Happy New Year. He asked me if I had any champagne left over. Yeah, we have half a bottle still in the refrigerator. He said, well, pour yourself a glass. We've just gotten the first pictures back from Hubble. And it worked. And of course, you all know that it worked. This is not a suspense story because it's been going now. That was back in December of 1993. So, but the amazing thing, that was just the start of the history of, the incredible work that Hubble has done, you know, these famous pillars of creation, which I still get goosebumps looking at them. I mean, the creation of stars, you know, let there be light. It's almost biblical. And then the death of stars, these incredible planetary nebula, which these stars' atmospheres get thrown out. I mean, it looks like the work of some psychedelic artist. But, you know, that's the universe. You know, that's real. We live in it. And Hubble has done an incredible job at making all of these pictures freely available to anyone, anywhere in the world. I'll just finish with what I think is the most incredible result that's come from Hubble. And of course, there have been many, many conferences about the science that has been done with Hubble. But, you know, one of this Hubble deep field, where they pointed Hubble for 10 days of observation at a tiny piece of sky that looked pretty much blank in most telescopes, and there were thousands of galaxies. And of course, you then can study these galaxies and learn more about the expansion of the universe, which Hubble had first discovered back in the early 20th century. And one of the big questions was, you know, with all the gravity of all the matter in the universe, the expansion of the universe should be slowing down slightly. But the rate at which it would be slowing down, we couldn't really measure until we got these images where, because the farther away the galaxies are, the more precise you could do these cosmological measurements. So they assigned 2 teams specifically to solve this problem. What is the rate at which the expansion of the universe is slowing down? And they didn't publish anything for over a year. You know, what was going on? They finally got together, and the reason they hadn't published was because neither one of them believed what they were finding. And hopefully you're all aware of this now, that the expansion of the universe is not slowing down, it's actually accelerating. And so they postulate this new dark energy, which is some force, and then using other kinds of telescopes and measuring the cosmic ray background, they come up with the result that this dark energy is almost 3/4 of the content of the universe. And we don't have a clue what it is. I mean, it's nice to give it a name. It makes it sound like you know what you're talking about, but we really don't have a clue what dark energy is. And then, of course, we have the cold dark matter, which astronomers have known about for quite a long time. That's almost, again, 1/4 of the universe. And everything, and I'm sorry to tell you this, but everything that you've been studying in physics and chemistry is only 4% of the universe. So, you know, I don't know what to do with that, but it's certainly, you know, that's what makes science fun, isn't it? You know, you solve a problem and 2 more problems come up. But amazingly, Hubble is still going strong. Here it is, you know, 30 years later. Of course, we were the first servicing missions. There were a total of 5 servicing missions, and so the optics of Hubble we corrected, but the sensitivity of the instrumentation has constantly been upgraded, so that Hubble now has almost 1,000 times more sensitivity than when it was first launched, even if the optics had been perfect. And that's the real value of servicing, and that's the real takeaway. And it's why Hubble has been so productive from a scientific point of view in terms of the number of papers and PhDs and so on, because every time we visited Hubble, we leave it like a new, better telescope. And the last mission in 2009, they left it in great shape, and Hubble's still going strong. People ask me, how long is it going to be going? Can't tell you. It could fail tomorrow, or it could keep going for another 10 years. But, you know, all I can say, it was for me, both as an astronomer and an astronaut, being able to work on Hubble and fix it was certainly the thrill of a lifetime, and I never get tired of talking about it, and I'm certainly delighted to have been able to come here and share the experience with all of you. So.
Someone who's been high up there and who is still so humble reminds us that young people can reach what you have done from a humble position. And in fact, this morning there was a lecture called The Hubble Space Telescope. Did any of you attend, or is it still to come? Okay, so don't miss that one. Yes. Can you tell what that is? Is that you?
Yeah. Well, the Hubble is a wild idea of producing very, very cheap 0.5 meters telescopes, because, well, you know that we are facing such problems with mega constellations, with light pollution, and yeah, that's it. It's producing $5 million telescope, a space telescope, half a meter, 250 kilos, and well, that's it. It's like the CubeSats for space telescopes. And by the way, I was not the first to imagine the name the Hubble Space Telescope. Now there is a constellation which is called Bright, of nanosatellites, which originally was the Hubble Space Telescope. I didn't know it, but I was not that clever as I supposed.
Thank you, Professor Jordi, and I encourage you all to look up on the grid to know exactly when and where his talk is going to be. I think that the expansion of the universe and its velocity can be a topic of discussion during lunch. By the way, those who are unfamiliar with campus, the cafeteria is that way. Just follow the crowd, just the next building. And I'm not sure if we have time for questions now, or if we just go and approach Jeff during lunch. This is an unconference. We improvise the decisions, and we just decided we have 5 minutes for questions. Madam, do you need the mic? Yes, because this is recorded.
Hello. Well, first of all, thank you for such an interesting presentation and for being here, especially knowing that you're not getting paid for that. I'm Elena. I'm from Barcelona, from here. And my question is regarding the future of space, human space exploration. We are right now in an explosion of new ideas and a big change of human space exploration. We know in a few years the ISS is planned to be deorbited, and so maybe new commercial space stations will come up to low Earth orbit. There will be also human space exploration in the moon, in the future, maybe in Mars. So I wanted to know, what's your point of view? How do you see the future of human space exploration?
Boy, things are changing. Is this microphone okay? Getting through? I turned it on. Yeah. Yeah. I mean, it's an exciting time. It's also a very challenging time. I mean, just the Artemis program to return humans to the moon. When you think about it, it's more challenging than Apollo. I mean, Apollo, we just wanted to send somebody there and bring them back safely. Now we're talking about actually establishing a permanent scientific base on the moon. So it's, you know, NASA's being asked to go way beyond what Apollo did, but we don't have an Apollo budget to go along with that. And so the rate at which, you know, back in Apollo, we were flying every few months. We would fly a mission, and now there's 1 to 2 years before every mission, and it's a big challenge. And there's far less testing available than we had during Apollo. So You know, I think the level of risk, if anything, is probably higher than we had during Apollo now. I hope we can do it successfully. But, and as far as the commercial space stations, this will also be a new era. I mean, commercial space flight has definitely gotten started. Can the economy support several commercial space stations? I mean, I don't see NASA being an anchor tenant on, you know, more than one. We just don't know. Ultimately, when you get into commercial space, the market's going to make these decisions, and we'll see. So, yeah.
Hi, thank you for your presentation. I'm very humbled to be here listening to you. I would like to ask you more like a personal question. What thoughts did you have when you were like up there preparing the telescope during all those 8 hours of work? What thoughts did you have? What did you experience?
There is the standard astronaut's prayer before you go out to do something like that is, you know, please God, don't let me screw up. We didn't want to break anything on the telescope that wasn't already broken, but it is really amazing how the many hours of training, it gives you a really good feeling. You know, when you go out and I could say, geez, I know what I'm doing. I've done this before. And now, of course, I always remember my first spacewalk where I went out and I was on my way to the tool chest. I was facing down towards the shuttle, so I was just looking at you know, the things inside the shuttle's cargo bay and thinking to myself, wow, this really feels like the water tank. You know, it's really good training. And then I got all the tools up and I turned around and there was the earth and the sky and I said, oh my gosh, we're not in the water anymore, you know. But the training, and of course, all the problems that they throw at you when you're doing your training, it builds up a confidence that when something goes wrong in the real mission, and we had several significant problems, you know, the very first day we replaced the rate gyros and then the doors wouldn't close properly. And we would have lost the telescopes without that. So we had to figure out, you know, on the spot what was wrong and how we were going to fix it. But we did. And so everything, as they say, was happily ever after.
One last question.
Okay. So as is the last question, I think it's very convenient. I'm Javier from Cosmic Research. Here there are a lot of people that may go into space at the future, young professionals. So my question is more about a professional like you. What would be your comment, your words for the future people that will be dedicating its time for the space sector? Thank you.
If I understand, you're asking what sort of training should you try to get yourself to give yourself a chance of going into space?
Oh, it's more to give some inspiring words or something like this.
Inspiring words. I mean, what can I say? As we were talking about before, I mean, it's exciting. I mean, look, I know when I talk to my students at MIT about the Apollo program or even about Hubble, it's ancient history. You know, these are things that happened a long time ago. And I think it's great now that your generation hopefully has a chance once again to experience exploration beyond Earth and hopefully maybe even beyond the moon at some point. You know, it's a wide open field, and you know, our robotics are getting better and better. Incredible things. I had an experiment on the Perseverance rover that produced the MOXIE experiment, which produced oxygen on Mars for the first time. You know, we're thinking about future human habitation. You know, it's a cliche to say that the sky's the limit, but you know, there's a lot of exciting stuff going on. And then the other thing is that you can participate now in space exploration. You don't have to be a rocket scientist. I mean, we have biologists, medical doctors, you know, all sorts of bioastronautics, chemistry, you know, plant biology, all sorts of different disciplines. People are getting involved in space applications. So, you know, pursue your dreams, figure out what it is that gets you excited, and almost certainly there's some way of getting involved in space exploration almost from any, you know, any academic interest that you start out with. So with that, I just wish you, you know, good luck and great careers for all of you. We need, you know, I sort of did my part. It's up to you now. You know, we're turning it over, and there's a lot of cool stuff out there waiting to be done, and I envy you for, you know, your opportunities to be a part of it.
You encourage us to continue asking questions, right? Talking about questions, in the spirit of the SpaceUP conference, this is a place where we can ask questions to Jeff, but also to everyone else. And the way to do that is, if you have a question that you think someone can answer within the group today, you can go to the check-in desk and write your question on the board, the same board where the grid is posted. You might already see, I'm aware of one question. Someone said, how do fluids behave in space, in microgravity?
Oh boy, that's
and
a
Geoff,
big one.
you know a lot about that. So there might be someone here, in addition to Jeff, who knows about fluids in space. And if you have other questions, post them there. Maybe we can improvise a specific talk or even a round table. And with this, let's give a very loud one so that they can hear it up at the ISS. An applause to Jeff.